Hi, just wanted to do a quick video for you about connected rates of change, mainly because the example is very nice from the textbook. So it's this one, which I'll show you. The head of a snowman of radius r loses volume by evaporation at rate proportional to its surface area. Assuming that the head is spherical, that the volume of a sphere is 4/3 pi r cubed. It's not an assumption, it just is, by the way. Surface area is 4 pi r squared. Write down a differential equation for the rate of change of the radius of the snowman's head. So it's a really practical situation. And notice his first sentence is believable, that the more contact area you have between the snowman's head and the surroundings, the more volume you're going to lose. If you study chemistry or physics, it's definitely a plausible assumption. The head's not going to be perfectly spherical, but as I say, the other two bits aren't assumptions, they're just true. That is the volume of the sphere, and that is its surface area. So let's look at the question, and let's look at how to approach it. So we know, start by writing down what you know. dV by dt is proportional to minus A. And that minus because it's losing volume in proportional to its surface area, which I've given a capital A. So in maths, we see this proportional sign. We want to replace that with an equals k. So dV by dt equals minus k, where k is some positive constant of proportionality, multiplied by the surface area. So write down what you know, and then write down what you need to know. We're asked for a differential equation for the rate of change of the radius of snowman's head. That's dr dt, the rate of change. And if it's a differential equation, we want dr by dt as a function of r. So let's look at how we get there. So like you've seen, using the chain rule from differentiation, dr dt is dr d something times dr dt. What information do we have that can help us? Aha! There's dv dt is minus ka. So if we put a dv here and a dv here, great. This is a true statement by the chain rule. Now, you should be thinking dv dt, that's minus ka. That's not a function of r, it's got a in, and a is a variable. Good thought, but hold it for a moment. Because first let's calculate dr dv. So the volume is 4/3 pi r cubed. So if we differentiate with respect to r, 3 comes down, cancel with that one, we get 4 pi r squared. So dV by dr is 4 pi r squared. We want dr by dV. That's 1 over that. So it's 1 over 4 pi r squared. So you might be thinking dr by dV is a function of r, but dV by dt is a function of a. If you are, well done. That's a good thought. But, funnily enough, a is 4 pi r squared. Here's 4 pi r squared too. So in fact, when we substitute everything in this side of the page, dr by dt is 1 over 4 pi r squared minus k times a, the surface area. The a is a problem, but it's not a problem because a is 4 pi r squared. So in fact, the 4 pi r squareds cancel, and it is a function of r, but that function of r is just minus k. So it's independent of r, but that's what we get. So there is no other variable in our expression. dr by dt is given by minus k, which is quite nice. I think this is a nice question, and the reason I think that is that we've got a situation. All this stuff is believable in the question, and we can establish that if you filmed a snowman's head melting in the snow, according to melting in the weather, according to these assumptions, the radius will reduce at a constant rate. So we're linking together here 3 variables, theoretically r, a, and v. They're obviously dependent on one another. And we can see that given this information of the question, dr by dt equals minus k. So the radius of the snowman's head is constantly reducing at the same rate until it is no more. So, like I say, I believe this is a nice question. I wanted to give you a quick example of how we can use connected rates of change in a problem situation to get an interesting result.